And we made plenty of carbocations before, so we have many ways to make carbocations. Actually, the newest way is complexing your alkyl halide with Lewis acid and then getting the halogen to leave. Okay? That's actually the newer of the ways. That's actually the most common when doing a Friedel-Crafts alkylation reaction. The most common way to form the carbocation halide complexing with Lewis acid. And the chlorine is the most common, mainly because it's the cheapest. And with chlorine, aluminum trichloride is the most common Lewis acid. Okay. All right. Friedel-Crafts reactions have a number of limits or problems. Limitations. Let's look at these. Number one, Friedel-Crafts reaction fails with strongly deactivating substituents. Now, your strongly deactivating substituents are also they're metadirectors. So we can't just refer to them as metadirectors. For example, if you try to do a Friedel-Crafts alkylation with nitrobenzene, it won't react because the nitro is a strongly deactivating substituent. Now you can do an EAS with nitrobenzene. You can like nitrate it again. You can brominate it, bromine and FeBr3 or something. So we'll do an EAS, but for some reason it won't do Friedel-Crafts EAS. It won't react with a carbocation. That implies that reacting with a carbocation is maybe more difficult than those other reactions. And there's some cutoff and it won't react with a carbocation. Can't really explain why beyond that. But we know that it doesn't. Fails with strongly deactivating substituents. In fact, nitrobenzene is sometimes used as a solvent for Friedel-Crafts reactions, where it's inert but some other aromatic reacts. All right? So, you can't do any Friedel-Crafts with strongly deactivating subs. No, don't do it. Won't work. Number two, reaction fails with anilines. Aniline will not do a Friedel-Crafts. Try to put an isopropyl group on here by forming the isopropyl cations. It's not going to react. Why not? Well, the NH2 is not a strongly deactivating substituent. Or is it? Because what happens here is, what's the mechanism here if we're going to do a Friedel-Crafts? What's the first step? What's the mechanism? The chlorine of your alkyl halide complexes with the aluminum? That? Okay. Well, instead, what about these electrons adding to the aluminum? I mean, why do those electrons but not these? Because this amine, although it is conjugated, it is somewhat basic, slightly basic. In organic 1, we said not basic. A lone pair conjugated, not basic. This aniline is slightly basic. And it will do this. You can't say, okay, nitrogen, we don't want you to coordinate with the aluminum. We only want the chlorine to. It won't listen to you. And once it coordinates, what type of group do we now have bonded to the ring? Strong deactivating, because now the nitrogen has a positive charge. And this is an equilibrium. But the equilibrium apparently heavily favors this. And so it essentially behaves as if it's this. And if it's this, I ask you to refer back to limitation number 1. And what does limitation number 1 say? Fails with strongly deactivating subs. See, under these conditions, the amine is a strongly deactivating substituent because it's complex with the aluminum. Now you can do it with phenol. And you say, well, doesn't the oxygen have a lone pair? Can't the oxygen lone pair coordinate with the aluminum? Theoretically, yes. But apparently it doesn't coordinate significantly. Because we know oxygen is not as basic as nitrogen. And of course, something like an alkyl group, like toluene. That's okay, because the methyl is not going to coordinate with the aluminum. It has no lone pair. So, no metal directors, because it's strongly deactivating. The only other one is, you can't do anilines, because they're basic enough to coordinate. Everything else is okay. I showed you 2 examples, but anything else is okay. If the nitrogen is an amide, this is okay. Because this lone pair is much less basic because it's also now conjugated with the carbonyl. And this does not apparently coordinate with the aluminum trichloride enough to kill the reaction. Only the free amines. Okay, so some limitations. Another limitation is rearrangement. Because in organic 1, we learned that carbocations are prone to doing what?
Rearranging.
Rearranging. If you take benzene and do a Friedel-Crafts with this alkyl chloride, aluminum trichloride, and we need to talk about this because it sort of goes against a rule that I told you to sort of never going to do. You actually get a mixture of products. You get 35% of this sort of straight chain butyl, but you get 65% of this here, where here the ring is bonded to the N carbon, here it's bonded to the second carbon. Well, how do we get these products? This coordinates with aluminum. I'm going to go ahead and show it coordinated. Can I just do that? That's it, coordinated with the aluminum trichloride. What do we do next?
The leaves.
You want to just leave? Forming leaves? What are we forming? What did we just form?
Primary carbocation.
A primary carbocation, which I told you 5 seconds ago that I remember we used to say never form primary carbocations. Now perhaps this ring attacks this carbon and kicks this off, sort of almost like an SN2, but it ain't an SN2, but it's a concerted sort of attack. Because we have done that, because whenever we chlorinated benzene, didn't we attack the chlorine complex with the Lewis acid? And didn't this attack here and kick that off? That's how we did halogenation. Because this didn't leave and make chlorine plus. We did not make chlorine plus. And so perhaps this could attack this carbon and kick off the chlorine, as opposed to attacking the chlorine and kicking off the chlorine. But if it did that, how would you get the other product? How does the other product come about?
A carbocation rearrangement?
Right. Because this can rearrange these electrons, we break them free and move them over here. And we get that carbocation, 1H remaining on the carbocation. Go from primary to secondary. And then the benzene ring can attack. Right? And it's the same old mechanism. The benzene ring has made a bond to I'm rotated here. Right? We make this bond. We're going to leave adjacent carbocation. Right? You should be able to finish this up on your own. You've got to know these details here. I can't sit here and just repeat it. We've already gone through them. There's an H here, and then something takes the H. In fact, what would you have take the H? These electrons here take the H, yeah? Move in. We get that product, and we reform what? Plus HCl, right? Aluminum trichloride is the catalyst. It's reformed. Now, my recommendation, what I hope that you're doing is you're really not writing any of this down. All this you already know, and to try to write it down in 30 seconds is just not useful. This is all just, we've already done this. You need to be, this is what's new. This is just, you should not be writing this down in my mind. This is the stuff that you do outside of class. Okay? It's the same old mechanism, EAS mechanism. To me, you should just be seeing this and say, yeah, okay, yeah. And if you don't know it, then you work on it some other time. The key thing here is, apparently, because this is real live data here, apparently this thing, it rearranges. But here's the key point. The fact that you get some rearranged product means you must have had primary cation. Because if the primary cation never formed, then you would never be getting a rearranged product. So this sort of proves that what I told you, never formed primary carbocation, is really not right. I tell you things to keep you out of trouble, but sometimes we do have to do them. I don't want to lie to you and never show this outcome. But be careful. You got to be very cautious about forming primary carbocations along the way. Apparently here it is. Yeah. Okay. I label this as compound A. The key thing here is if you wanted to make A here, you're not going to get a good yield because of rearrangements. You're going to get more of this product. And so that's a limitation. Of course, it's only a limitation if you want A. If you actually want this product, then this is not a limitation. It's good. All depends on what you want. On the next page or two, we will see a better route to make A. This is called a direct or alkylation. Minor product. Major is, and remember we said before, anytime you can do a carbocation rearrangement, That's what we want to do? Yeah. This product would be our predicted. Would this rearrange again? Could it rearrange some other? What if this H moved here?
It's the same.
It'd be the same carbocation. These are the only two possible products. Because cation here is the same as the original, and cation there is the same as this one. Okay, so always be on the lookout for rearrangements. Another limitation is polyalkylation. Polyalkylation. If you take benzene and you try to make isopropyl benzene, which actually does have a common name. Methylbenzene is toluene. Isopropyl benzene, I'm pretty sure is called cumene, but you don't need to know that. A lot of common names with benzene compounds. So if you want to try to make cumene here by isopropyl, okay, complexing, the key electrophile here, what's the electrophile? The carbocation, you know how to get there, right? The ring attacks, okay? EAS mechanism. The problem is you're not going to get a good yield of cumene because it's going to react again. Just going to react again. And, we have a group here. What type of director is this isopropyl?
Group 2.
Group 2.
Or, I mean, orthopara.
Orthopara. Okay? I put the next group para. Okay? Now you may also get some ortho for the second. Okay? Although Frito crafts tend to prefer para. You do have sterics here that may make it favor para over ortho. This also tends to be a large species, that carbocation, because it often has substituents on it. Okay, so this is fairly large. And it may have even more trouble getting next to the ortho position because you got two alkyl groups there. Okay? And the bigger your carbocation gets, the more it just favors para. Frito crafts often favor para a good bit. Why does it react again? Which is more reactive towards EES, the starting material here or the product? This first. Which is more reactive towards EAS?
The product?
Because we put on an alkyl group. What does the alkyl group do in terms of its...
Weakly activate?
It's activating. Isopropyl benzene is more reactive in an EAS reaction than benzene. Because we added an activating group. Think about this. When this reaction goes 10%, and you got 90 of this, and 10% of this. Then you're like, okay, benzene, keep reacting here. And we want to convert all of you to that. Well, guess what? This guy, once it starts forming, is going to come react over here. And which reacts faster? Right or left?
Right.
Right.
Right. The thing you're making is going to start reacting with this instead of that. You can't say, okay, isopropyl benzene, we've made you. We know you're more reactive than benzene, but we want you to just not react. It won't listen to you. And it reacts again. Now we've got two groups. Now this is more reactive than that. Two activating groups. And it reacts again. Now you've got three groups. And it's more and more reactive. And it just keeps on. Even if you use one equivalent. Even if you just try to use one equivalent of stuff, again, 10% this, and this 10% just reacts again. If you only use one equivalent, you're going to be left with some of this that never had a chance to react. Okay? It becomes a mess. You just get polyalkylation. It's very difficult. Now, in practice, you can sometimes get a good yield of this by using a huge amount of this. And that way, even though this is formed, there's still a huge amount of this that it just makes it more prone to react. But if you do that, you're going to be left with a huge amount of this at the end. You can do that if this is easy to get rid of. And if it's easy to separate from this. And sometimes in practice, that's very doable. That practical stuff is a little bit more difficult to try to explain. And we don't really need to, right now, understand the limitation. But sometimes you may see a decent yield of this out there somewhere, but it was done in a certain way to overcome this limitation. Okay? Question? There's a few limitations here, yeah? But we're gonna sort of solve this in a minute. And it's time to solve it now. Time to solve some of these limitations by looking at Friedel Crafts acylation. Acylation. An acyl group is a general name for a carbonyl group, ketone. Yeah.
Is there a way you can poison that previous reaction?
And make it stop,
Yes.
sort of like you're referring to like alkyne being hydrogenated to alkene.
Yes, sir.
And regular catalyst, it goes all the way. There's nothing that I know of a poison. There is practical ways to do it that I mentioned that allow you to get a decent yield by, for example, using a lot of the starting material. Now, even though that's more reactive that you just made, if there's a huge amount of this, it still sort of wins out. Okay, acyl group has the carbonyl. Not an alkyl, not an alkylation, but an acylation. Carbonyl is bonded to the ring. Very darn similar. Instead of using an alkyl chloride, we use an acyl chloride. All right? Acyl chloride. And this may be the first time we've ever used acyl chlorides. They're pretty common, and we will use them over during test 3 a good bit when we start doing carbonyl chemistry. I think it was on the functional group list in Organic 1. Yeah? But they're super common, first time we use them. Also known as an acid chloride. Because they're made from the OH. If this was an OH, that would be a carboxylic acid. They're made from carboxylic acid, so they're often called acid chlorides. All right? And I would probably use that name more. Now I'll go ahead and say here, the R group here, connected to the carbonyl, can be sp3 or sp2 carbon. There's really not many restrictions here at all. But it can't be H. Because if this was H, that's not a stable molecule. I'll point that out because some of you down the road try to use that molecule, and as you try to design a reaction, I'm telling you right now, it's just not stable and not useful. And that may come up a little bit later. And I'll say, remember what we said over there? Okay. So mechanism, very similar as the alkylation. The chlorine complexes with the Lewis acid. And we get to this here. And then this chlorine leaves. Hey, I need my electrons back. I'm going to leave. One molecule becoming two, driven by entropy. Okay. What does this form here, though? What is this here? First off, it's a carbon cation, so it is a carbocation. What is that, though? Does that have any stability? What is?
Resonance stabilized?
Isn't it like basically an alpha cleavage?
We've seen this in mass spec before. Mass spec. And this is resonance stabilized. You can do resonance. Now my bond angle is wrong here. What's the hybridization of the carbon here?
SP2.
What's the hybridization of that carbon? How many regions around it?
3.
How many regions around it? Just 2. Double bond regions, single bond regions. 2 regions. What's hybridization? SP. Geometry? Linear. Okay. It's actually linear now. See, when this chlorine leaves, the oxygen actually goes down and that becomes linear. Now, I just kind of drew it like that because it was drawn like that. But the real here is it's really linear. Understand your hybridization, okay? It's the same old questions. Now, when we draw the resonance structure, typically then I will draw it, guess what? Linear. It's supposed to be linear there. Those electrons just move in, and now what do we have here? The carbon is now neutral. One lone pair here, but now the oxygen is positive. And we've seen this before in mass spec. What's the name of this type of ion?
Alpha cleavage.
Psyllium ion.
Yes. A psyllium ion. Before we've only formed this in mass spec of ketones. Here we're forming an acylium ion in a mechanism. Which is the major resonance structure of the acylium ion?
Left.
I didn't do that one.
Why this one?
Because the charge is on the
Charge is
board.
better on the oxygen and the carbon.
Well, that's actually not the good reason. You'd rather oxygen doesn't want to be positive. Carbon is more likely to be positive.
More bonds. More bonds.
More bonds. More bonds. That's the reason. Remember, these elements to the right of carbon will take on a positive charge as long as they have an octet. Does the oxygen have an octet over here? Yes. As long as it has an octet, you can do resonance and have a positive, even a positive fluorine. Has an octet. Major resonance structure. All right, acylium ion formed here. Well, guess what? The ring then attacks the acylium ion. Same old mechanism. You have to set this up and get your pi bond right, and then you can attack. When you attack, you don't have to do anything. Now, you could attack. Of course, the true structure is a blend. You're always going to attack the carbon. All right? You can always work with any resonance structure. And if this is the major one, you might say, well, why don't we work with it? Well, you can. This just sort of looks more like the product. Here, the pi electrons are going to attack the carbon and move these back. If you want to use this resonance structure, in the end, you make it a carbon-carbon bond here. Okay? Carbon-carbon bond here. Some of you guys, I see, you want to maybe attack the oxygen because it's positive. But if you look at that, that leads to a carbon negative. The electrons are flowing this way. See my dipole light drip here? The electrons want to be pushed back toward the oxygen, and the chemistry comes this way. Or you just react here. All right? It's a carbon-carbon bond reaction. And then you lose the proton. Something takes the proton, you get to HCl, and then plus the catalyst reform, right? It's the same old thing. Once we form our electrophile, you know the EAS mechanism. And we actually, we get a carbonyl binder to the ring. Example. You take benzene with this acid chloride, aluminum trichloride, you can get this ketone product. Very nice reaction to make this ketone. Do we have to worry about polyalkylation? Or in this case, it would be called polyacylation. Do we have to worry about a second reaction? Why not, Jen?
Because
What type of group are we adding to the ring? Is this an activator?
No, it's deactivator.
Strong deactivator.
It's actually a strong deactivator. And what did we learn on the previous about strong deactivators?
It's a limitation for Friedel crafts.
They don't do Friedel crafts. So you don't have to worry about polyacylation. Acylation is a much better reaction, a much higher yielding reaction, because of this being one of the reasons. You're adding the deactivating group. Okay. A secondary here. The carbonyl here that's bonded to the benzene ring, this oxygen can be removed. This carbon can be reduced. It can be reduced using hydrogenation, such as hydrogen and palladium, or platinum, or nickel. One, two, three, four. 1, 2, 3, 4. This used to have an oxygen. Now there's 2 H's here. Hydrogen gas will do this. We will not look at a mechanism. Another way to do this, it's actually 3 ways to do this. This is classical textbook. Next one. A combination of zinc and mercury amalgam. And HCl. This is like a dissolving metal reduction. We know when we add H's, that's a reduction. This carbon has 2 bonds to a more electronegative atom. Now the carbon has no bonds to a more electronegative atom. It's been reduced. Hydrogenation. Dissolving metal reduction. Some of you guys have used zinc in the lab. I wish all of you had used it. Zinc and a proton source, a reduction. This reduction is a little bit more difficult than a nitro reduction. And by the way, when we reduce a nitro group to the amino group, aren't we removing oxygens and replacing it with H's? It's a lot what we're doing here. We're removing an oxygen from the carbon, replacing it with H's. Again, we're not looking at detailed mechanism. A little bit more difficult And the mercury mixed with the zinc really helps. It makes it more specialized than just plain zinc. Okay? But zinc mercury with ACl is called a Clemmensen reduction. Clemmensen reduction is very common for reducing the conjugated aryl ketone to the alkane, basically removing the oxygen. A third way to do it is called the Wolff-Kishner reduction. This uses hydrazine and hydroxide. We will look at this mechanism during test 4 material. When we look specifically at aldehyde ketone chemistry, we will look at this mechanism later. For now, you just sort of know the reagents. That's hydrazine. N2H4 is hydrazine. It's sort of the nitrogen analog of hydrogen peroxide. And just like peroxide being pretty reactive and it can be explosive, hydrazine can be explosive. Nitrogens bind to each other. They don't like to bond to each other. Oxygens don't like to bond to each other. Hydrazine is used as a rocket fuel, or it used to be a long time ago. Very bustable and high energy bond here. But it can be used safely in the lab. Okay. So it's a very sort of important transformation. A, remember when we tried to make compound A on the previous page and the yield was low? Because the carbocation rearranged. You don't have to worry about rearrangements here. The acylium ion is not going to rearrange because it's resonance stabilized. So no polyacylation, no rearrangements. Acylation is a much better reaction. And compound A can be made in a much higher yield by this two-step process. Acylation followed by reduction. Much better way to get an alkyl group on. Okay? Acylation followed by reduction, two-step group gives a higher yield of A than the one-step alkylation. And here's the take-home again. Anytime you want to put an alkyl group on, the best way to do it is to acylate, then reduce. You just have to keep in mind that the acyl, the carbonyl becomes a CH2. And so 4 carbon chain, 4 carbon chain. All right? Now, some of you will try to use this chemistry to make an aldehyde by maybe trying to use this. Let's see, if I complex with the aluminum, this ionizes, I'll get this acylium ion, and then the ring can attack that acylium ion. Again, the problem is this is not stable, so you can't use it. But you can produce that in situ by reacting carbon monoxide and HCl. These produces that in situ. And so this does give the aldehyde if you consider that. Okay? You could even show a mechanism for how these two react to give that molecule. should be pretty straightforward if you just draw out your Lewis structures and consider what needs to react where to give this. And see, that's an equilibrium. The reason you cannot have this, if you just had this molecule somehow, which you cannot, but if you did, it would just break down, it would decompose, and it would turn into CO and HCl. And if you, that would establish an equilibrium in the bottle. But what happens when you take the bottle cap off? These two gases are going to escape. And if this escapes, what happens to your equilibrium? What did Le Chatelet tell us would happen? It would adjust to replace this. So as this escapes, more of this comes this way. As this escapes, more of this comes this way. And when all this escapes, all that's gone. And eventually everything just goes off as CO and HCl because it escapes and the equilibrium goes to that side to help. Right? Chatelet knew what he was talking about, right? More importantly, do you understand what I just said?
Yeah.
Just an application of Le Chatelet. But it's the practical stuff. All right? How does this practically lead to nothing being there? Well, you take the cap off. Now things can escape. Those gases will escape if you take the cap off. Okay, big products. In the end, acylation is it's a much better reaction. What limitations did we not solve? We solved polyalkylation, because polyacylation doesn't take place. We solved the rearrangements. What we did not solve is you still cannot react something like nitrobenzene or anilines. Those will not do an acylation either. Nitrobenzene, etc., and aniline will not do any Friedel-Crafts reaction. Okay. You can predict products here. Somebody have a product for the first one? Somebody have a product for the first one?
Wouldn't
Wouldn't it be no
two
reaction?
benzene rings with a ketone in the middle, and then pair it to that ketone, or pair it to the carbonyl as the fluorine?
I think you might have it. Why did you say no reaction, Jim?
Because it's a strongly deactivating group. I thought we just said that you can't do Friedel-Crafts unless this is like not a Friedel-Crafts reaction. We're just not recognizing it.
No, the F is not a strongly deactivated group. The F is only a mildly deactivated group. F is group 3.
I meant like on the original reaction with the carbonyl and the chloride.
Yeah, but this is not the ring that's reacting. This is the alkyl chloride, the carbonyl chloride. This is the ring that's reacting.
So just like flip them, and then you probably look better.
All right, I designed this reaction to bring about this consideration. Which ring is reacting here?
It's the carbonyl and then the benzene ring.
Well, let's first do the chemistry. What mechanistically, what happens first?
The chlorine attacks the aluminum, and then it leaves, and you're left with the...
Jen, do you agree that the first step is this
Yes, I agree.
here?
Mm-hmm.
Yeah? And this leaves to give the acylium ion. We can draw resonance structure, but we can just not draw resonance structure. Now, what reacts with the acylium ion?
The benzene ring with the
this ring. And this ring has an F, which is not a strongly deactivating group. It's group 3, weakly deactivated. It will do Friedel Crafts. What type of director is the F?
Para ortho. By para mostly.
Ortho-para director. Groups 1 through 3 are ortho-para directors. And so product here is going to be, you can work through your mechanism. That there, which is para to the F, plus we were also going to get what?
Some ortho.
Plus ortho. I'll let you draw that on your own. We made this bond here. That ring attacks EAS mechanism. You need to sit down and go through it. This ring is not doing EAS. This ring is just on the acyl chloride. That's an example back over here. Where the R group is just sp2. That R group can be a benzene ring. And so you can have 2 benzene rings, but you got to understand that only one of them is going to be reactive. Because you are right with what you said, Jen. That ring actually does have a strongly deactivating group, so it's not going to be reactive. But we had that fluorobenzene that will be reactive. Okay, guys, quiz on Wednesday. Up through this point, we will include Friedel-Crafts reactions. Have a good day, guys.
Yeah, right.